Hello friends, welcome back to Webronaq. Now look at this. Every smartphone, every laptop, every gaming console, every server running the internet, they all have one thing in common. Inside their processors, billions of tiny things called logic gates are doing all the work. And here's the wild part. These logic gates only know how to do one thing. They take in some signals and they decide yes or no. That's it. That's the entire foundation of computing. So in this video, let's break down what a logic gate actually is, look at the main types you need to know, and see how stacking these simple yes or no decisions ends up powering literally every computer on the planet. Let's get into it.
All right, let me show you the simplest way to think about a logic gate. Imagine a light switch on your wall. When the switch is off, no current flows. The bulb stays dark. When you flip it on, current flows and the bulb lights up. Off and on. That's it. Now, in the world of computers, we don't say off and on, we say 0 and 1. 0 means no signal, 1 means there is a signal. And a logic gate is just a tiny electronic device that takes one or more of these zeros and ones as input, applies a simple rule, and gives you a single 0 or 1 as output. That's the whole job. The magic isn't in any one gate, the magic is in the rule each gate follows. Different rule, different gate. So let's look at the three most important ones. First up, the AND gate. The rule here is simple. The output is 1 only when both inputs are 1. If even one of the inputs is 0, the output is 0. Think of it like the safety system on a microwave. The microwave only starts heating when the door is closed and you've pressed start. If the door is open, nothing happens. If you haven't pressed start, nothing happens. Both conditions have to be true at the same time. That's exactly how an AND gate behaves. Look at this truth table on the right. It shows every possible combination of two inputs, A and B, and the output Y for each. 0 and 0 gives 0. 0 and 1 gives 0. 1 and 0 gives 0. And only when both A and B are 1, the output finally becomes 1. Simple rule, but it's used everywhere inside a CPU.
Next, the OR gate. This one's the opposite vibe of the AND gate. The OR gate gives you a 1 if at least one input is a 1. Both inputs 0, output is 0. But the moment any input becomes 1, the output flips to 1. Think about how you unlock your phone. You can unlock it with your fingerprint, or with your face, or with your PIN. You don't need all three. Any one of them is enough. That's an OR gate in action. Look at the truth table. Only the very first row, where both inputs are 0, gives you a 0 output. Every other combination produces a 1. So if AND is the strict gate that needs everything, OR is the generous gate that's happy with anything. And now the third one, the NOT gate. This one is the simplest of all. It takes just one input, and it flips it. If the input is 0, the output is 1. If the input is 1, the output is 0. That's it. It's basically a no, do the opposite button. You've already seen this logic in action. Think of the mute button on YouTube. If the video is unmuted and you click mute, it becomes muted. If it's muted and you click it again, it becomes unmuted. The button just flips whatever the current state is. That's a NOT gate. And notice that little bubble at the tip of the triangle in the symbol? Anywhere you see that bubble in a circuit diagram, it means inversion is happening. Keep an eye on that bubble, because it's about to show up again in the next two gates. All right, now let's combine what we've just learned. If you take an AND gate and stick a NOT gate at the end of it, you get a NAND gate, short for not AND. The output is just the AND gate's result flipped. So instead of giving you a 1 only when both inputs are 1, NAND gives you a 0 only when both inputs are 1. Every other combination produces a 1. Same idea with the NOR gate. That's an OR gate followed by a NOT. So the OR gate's output gets flipped. Now, here's why these two are a big deal. NAND and NOR are called universal gates because you can build literally any other logic gate using just NANDs or just NORs. And, or, NOT, all of them can be constructed by chaining NAND gates together in clever ways. That's huge for chip manufacturers because it means a factory can mass produce just one type of gate and still build any digital circuit on the planet. Cheaper, simpler, and easier to scale.
Now, the most interesting gate of the bunch, the XOR gate, or exclusive OR. The rule here is beautifully simple. The output is 1 only when the two inputs are different from each other. If both inputs are the same, both 0 or both 1, the output is 0. If they're different, the output is 1. So XOR is basically a spot the difference gate. And here's why this gate matters so much. When your CPU adds two binary numbers together, XOR is doing the actual addition work. Remember from our earlier video on binary, when you add 1 plus 1 in binary, you get 1, 0. The result digit is 0 and you carry a 1. That 0 you see in the result, that's literally an XOR gate's output. The carry, that's an AND gate's output. So every time your calculator adds two numbers, every time a game updates a score, every time your bank app calculates a balance, XOR gates are quietly doing the math. One simple rule, powering every addition operation in your computer.
So now, zoom out with me for a second. One logic gate on its own can only answer one tiny yes or no question. Pretty boring, right? But here's where it gets wild. When you connect a few gates together, you can build something that adds two binary numbers. That's called an adder. Connect a few more, and you can build something that remembers a 1 or a 0. That's a memory cell. Connect thousands of these together, and you've built a calculator. Connect millions, and you've built the unit that runs instructions and does math inside a processor. And the chip inside your phone or laptop right now, it has billions of these tiny logic gates etched onto a piece of silicon smaller than your fingernail. Apple's M-series chips, Intel's latest processors, the chip inside your gaming console. All of them are just unimaginably massive arrangements of AND, OR, NOT, and XOR gates, all switching on and off billions of times per second. That's the entire trick of computing. Simple rules repeated at insane scale. So that's the full picture. AND, OR, NOT, your three core gates. NAND and NOR, the universal ones that can build anything. XOR, the gate that makes addition possible. And there's one more I haven't mentioned. XNOR, which is just XOR with a NOT at the end. It gives you a 1 when the inputs are the same. That's all 7. Every app you open, every video you stream, every line of code you'll ever write, it all comes down to billions of these tiny gates flipping between 0 and 1. Pretty mind-blowing when you really think about it. If this video helped you finally understand what's happening inside a CPU, hit that subscribe button and smash the like. It genuinely helps the channel grow. And I'll catch you in the next video.